we are going to look at applying Poisson distribution for events that occur at certain points in time. So let me give some examples of events that we are looking at. So number of earthquakes occurring during some fixed period of time, a number of wars per year, number of deaths in a given period of time of policyholders of a life insurance company, number of electrons emitted from a heated cathode during a fixed time period. So I'm going to describe this application in two examples, and in the next video we will discuss underlying assumptions that are needed to justify this application. So when I say time period, I mean unit of time. So here's an example. Suppose earthquakes occur in the western part of US at a rate of 2 per week. Now when the question says at a rate of 2 per week, what it means is that on average we expect to see 2 earthquakes per week. On average we expect to see 2 earthquakes per week. So this 2 is the expectation of the number of earthquakes per week. Okay, so we want to find the probability that at least 3 earthquakes occur during next to week. And so in order to find that, I'm going to first of all define a variable x, and x will be the number of earthquakes over 2 weeks. Well, then what would be the expectation of x? The expectation of x would be, notice that the expectation of, we know that the expectation of number of earthquakes per week is 2. So this is a rate of 2 per week. So that means over 2 weeks we expect to see 2 times 2 or 4 earthquakes, and I'm going to let lambda to be 4, and this count x, the count of number of earthquakes, follows a Poisson random variable. So x has Poisson distribution with parameter lambda, which is in this case 4, and so the PMF, the probability that x is k, is e to the minus lambda times lambda to the k over k factorial for any non-negative integer k. So remember, what we wanted to find is the probability that at least 3 earthquakes occur during next 2 weeks. Well, what it is asking us to find then is the probability that x is at least 3. That's the same as 1 minus the probability that x is strictly less than 3, which then is equal to 1 minus the probability that x is 0 plus the probability that x is 1, the probability that x is 2. And so we now plug in order to find the probability that x is 0, we plug in k to be 0 in the PMF of x. So what we get is 1 minus e to the negative 4 plus e to the negative 4 times 4 plus e to the negative 4 times 8. So then we get 1 minus 13 e to the negative 4. Okay, so that's the probability that x is larger or equal to 3. Okay, so let's ask a different question now. Let's let capital T, so we're defining a new random variable, capital T, and that's the amount of time in weeks, that is, it's the number of weeks until the next earthquake occurs. So T is the number of weeks until the next earthquake occurs, and what we want to do is find the CDF of cap T, that is, we want to find the function f of t, which is the same as the probability that cap T is less than or equal to T. So in order to find this, then let's start out in the following way. So we want to find f of t, which is the probability that x is less than or equal to lowercase t. Now, by using probability laws, we know this is the same as 1 minus the probability of the complement, which is x larger than t. Now, that's not x. This is capital T. This is capital T. So we want to find the probability that cap T is larger than small t. So if you think about this, cap T is the number of weeks until the next earthquake. So this event here says the number of weeks until the next earthquake occurs is more than t weeks, right? In other words, no earthquakes occur over the period from 0 to t. Okay. So what I'm saying is, once again, the event that cap T is larger than small t, it's the event that the number of weeks until the next earthquake occurs is more than t weeks, which is the same as saying that which is the same as the event that no earthquakes occur over the period from 0 to small t. So this is the same as saying 1 minus the probability that no earthquakes occur over the period from 0 to t. No over the period from 0 to small t, and this is equal to one minus the probability that x is 0 I need to make a little bit of a room here. Okay, so where x is the number of earthquakes over the period from 0 to t, well, over the period from 0 to t, then what's the expectation of x? So let lambda to be the expectation of x. Because the rate per week is 2, this would be 2 times t, and x is then a Poisson random variable with parameter lambda equals to 2t. So then we could say that the probability that x is 0 is e to the minus lambda, which is 2t, times lambda to the 0 divided by 0 factorial, which then is equal to 1 minus e to the negative 2t. Okay, so we have found the probability that cap t is at most t. Okay, so in the next video we will look at assumptions underlying this application of the Poisson distribution. That is, applying the Poisson distribution. What are the assumptions that are needed to apply Poisson distribution for the count of an event occurring over time? So we'll look at it in the next video.